All right, how's it going? So I completely spaced on your homework until 3 o'clock this morning. I woke up and I was like, oh no. I got so carried away grading 224. Completely forgot to grade 215. And I did debate getting up at 3 to grade it, but I decided not to. So I'll get it graded this afternoon.
What's today's homework?
The homework that you turned in last Wednesday that I had 5 days to grade. And because I had so much time, I didn't rush through it right away. And this is what happens, so. My bad. So it's been 5 days, and we only have 1 day this week because we only have classes today and tomorrow. So it's a short week after a short week. So any questions? We finished up with combinatorics and counting and stuff last week. Any lingering questions from any of that? Yeah.
Oh, wait, the segment?
Yeah.
Okay, I had a question on the detail. So when you're asking for the cardinality of A and B, do you mean like A cross B, or just A and then B?
Cardinality of A and then cardinality of B. So the number of elements in each of those sets. Yeah. And remember, don't count duplicates. Yeah.
Can we assume lowercase letters, or do we have to?
Yeah, everything that's input is going to be lowercase, but if you're using fgets, there's going to be a new line at the end, so get rid of that
Yeah.
some way.
Yeah, I emailed you that about that too.
Yeah. Yeah, I'll only test with lowercase letters.
Yeah.
Other questions? Is that programming assignment pretty doable?
I'm in trouble
I
with
hope so.
intersection.
Intersection?
Yeah.
So you have two sets in general, desert island. How do you tell what the intersection is?
Look at the same.
So here's a set of fruits, here's a set of fruits. You want to know what fruits are in common. How would you do it? Just like on a desert island, forget code.
Them together, I guess. I don't know.
Would you compare each one individually?
Probably compare each one individually. As soon as you put them together, you've lost information.
Oh, yeah.
But, so, let's find the intersection of,
Start with one set of fruits.
intersection of this set with that set, right? So two sets, how do we find what's in common? Well, I mean, we can just look and say blue, but a computer, right? So one way is grab the first element of this set and say, is it contained in this set? No, toss it out. Grab the next element of this set, is it contained in this set? Yes, it is, so that's part of the intersection, right? If we have this one, we grab this, is this contained in this set? Yes, it is, so that's also part of the intersection. And you grab another marker from here and it's not in that set, so you toss it out. So go through your first set and for each element, see if it's a member of the second set. And if it is, add that to your output set. Right, so it's really useful if you have a way to create an empty set and then add things to it. And then it becomes something like for each member of the first set, if it's in the second set, add it to the output. Otherwise, you potentially have this like n by n problem where you compare each thing here to each thing there, and that's not too bad. But other questions? All right, so let's talk about graph theory. So graph theory is one of these areas of computer science that can be very abstract. It's actually a branch of mathematics, graph theory. It's an area that has some questions that are very simple to ask and very difficult to answer, right? And so we want to look at some aspects of graph theory itself, but we also want to talk about graph theory in terms of computer science. What are some ways of representing these objects that we call graphs inside a computer? What are some algorithms we can use for answering questions about graphs, and so on and so forth. We're going to start with kind of a bit of the theory side of what graphs are and what they're made up of. So I'm going to write G as an ordered pair of sets V and E, and V is going to be called the vertices. And V cannot be empty. There's got to be at least one vertex. And E is the set of edges. And each edge, which is an element of E, has one or two endpoints. And the endpoints are vertices. So they're contained in V, and we say E connects its endpoints. So here's a simple example of a graph. All right, so we have 1, 2, 3, 4, 5 edges. We have 4 vertices. So this edge connects this and this vertex. Those are its two endpoints. This edge connects this vertex and this vertex. Those are its endpoints. There's no edge connecting this vertex to this vertex. Okay, so it's not as complex as the definition makes it sound. A graph is called simple if for any pair of vertices there is less than or equal to one edge connecting them. So this is a simple graph. If I were to add another edge like this, it's no longer simple because these two vertices are connected by two edges. And mostly we're going to deal with simple graphs. Technically up here we could have, a whole bunch of connections between the same pair of vertices and it's still a graph, but it's not simple. Right? So mostly we'll work with simple where we have at most one connection between any pair of vertices. So what are examples of graphs? Well, computer networks. So here's a bunch of connection points on the net, and there's connections between them. This could be a map of city streets, right? These could be crossroads, and these are roads connecting them, or these could be cities, and these are airline routes connecting different cities, right? There's all kinds of things that we can represent with a graph type structure. We can make an acquaintance graph where the vertices correspond to people, and a line between them means that they know each other. They're directly acquainted, right? And when we store information as a graph, we can start to analyze relationships. For example, this person and this person are not directly acquainted because there's no edge connecting this vertex to this vertex. But there is an edge connecting this vertex to this vertex and this to that. And so there's an indirect acquaintance. Yeah.
You say that each edge has one or two endpoints. What's
Mhm.
the case where we only have one? Sorry.
So you can have loops. So this person and that person are indirectly acquainted through this other person, right? So if you're on LinkedIn and you know somebody and they're like a direct link or someone who's 2 links away or 3 links away, right? There's a big association graph of who knows who, and the number of edges from one vertex to another basically tells you how closely you're related. And everybody's related if you go like 6 or 7 edges, right? So degrees of separation. So in some cases, we also associate a direction with these edges. So we might have something like this. Right, so let me label these vertices. A, B, C, D. So there's an edge from A to B, there's an edge from B to D, from B to C, from A to D, and also from D to A. But those are our only edges. So this is an example of a directed graph. And so each edge is given by an ordered pair. For example, AB might be this edge up here. And the ordering in this case is the first vertex is what we're coming from, the second vertex is what we're going to. So our graph might contain edges A comma B, B comma C, B comma D, A comma D, and D comma A.
So BA is just not part of this graph?
So BA is not a part of this graph because there's no edge from B to A. So this would be a street map of Portland where everything's a freaking one-way street, right? So you can get from A to B, but if you want to get from B to A, you got to go over to D, and then you got to go over to A, right? And there's lots of things we can identify with directed graphs. So you could make a org chart hierarchy, right? Who is whose boss? And A could be the boss of B, and B could be the boss of C and D, and so on. And this is weird because then D is the boss of A, but you know. So roadways, influence graphs, who has influence over whom, and so on and so forth. All right, so definitions. So two vertices, U and V, are adjacent. If they're connected by an edge. It's an edge E. And in this case, we say E is incident. Bless you. With U and V. And we can also say E connects U and V. So I'll label my edges with numbers. Alright, so A and B are adjacent vertices. They're connected by edge 4, so 4 is incident with A and it's incident with B and it connects A and B. So it's just terminology. Alright, N of V is the neighborhood of a vertex. And this is the set of all vertices U that are adjacent to V. So the neighborhood of A is B and G and C. It's all the vertices that are adjacent to A. So neighborhood of A is B, C, G. What's the neighborhood of B? Right, it's all the vertices that are adjacent to B. Someone else, neighborhood of C. GA. And anyone else, neighborhood of D. Just B. And neighborhood of G. AC. You got it. All right, so the degree of a vertex V, and we write it with a little hunchback D for degree. So degree of V is the number of edges incident to V. So the degree of A is the number of edges incident to it, so it looks like edges 1, 3, and 4 are incident. So that's 3. The degree of B is going to be 2, and so on. Degree of C is edges 1 and 2, so that's 2. Degree of D is just going to be 1 edge, so that's 1. The degree of E or G is 1, 2. Right, so it looks like the cardinality of the neighborhood gives you the degree.
Can you repeat the definition of degrees?
The degree of a vertex is the number of edges incident to it. And there's a caveat here, which is loops count twice. So if we have something like this, the degree of A would actually be 2. Even though there's a single edge, but there's an edge that starts at A and there's another edge that ends at A. They're the same edge, but we count it twice, so the degree of A would actually be 2. And that's just our footnote. And we're talking undirected graphs for now. So in this,
Are you
yeah,
talking about a stack graph up,
yeah,
or are you talking about degree of A equal?
up here,
Okay.
so separate graph. So we're ready for a theorem. So back on this graph with 5 vertices, A, B, C, D, G, we found the degree of each vertex. What's the sum of the degrees? Ten. All right, so 3, 2, 2, 2, 1. All right, so the sum of the degrees is 10. How many edges do we have in this graph? 5. 2 times 5 is 10. Okay, this is actually a theorem. So theorem in an undirected graph. Two times the number of edges is equal to the sum over each vertex contained in V of the degree of that vertex. That's a fancy way of writing. If you add up the degree of each vertex, you end up with twice the number of edges.
Does that change with the direction graph?
Yeah, it gets a little prettier with a directed graph. And we'll do that shortly. So there's a graph, 3 edges. What's the degree of each vertex? 2, so sum of the degrees will be 6. 2 times 3 is 6. So far, so good. So there's another graph. What's the degree of each vertex there? Count them up. Yeah, 3. So the degree is 3, 3, 3, 3. Add them up, that's 12. Total number of edges is 6. So that seems good. Let's put another vertex down here. So let me write my degrees up here. So this is 3, 3. This now has degree 4, 4, and 2. So 4, 6, 10, 14, 16. Sum of the degrees is equal to 16, and the number of edges 1, 2, 3, 4, 5, 6, 7, 8. So this looks promising. Could we prove it? Of course we can prove it. Could we use induction maybe? Probably. Induction's another big hammer. It's good for everything. We could probably induct on the number of edges. Because if we know that for 8 edges, the sum of the degrees will be 16, if we have one more edge, it's got to start somewhere, and it's got to end somewhere. And the degree of where it starts will go up by 1, and the degree of where it ends will go up by 1. So the sum of the degrees will go up by 2, and the number of edges goes up by 1. Well, if we know the original sum of the degrees was equal to twice the number of edges, and we know that the number of edges has gone up by 1 and the sum of the degrees has gone up by 2, then we know that the sum of the degrees in the new graph is equal to twice the new number of edges. So we can make a proposition that this is true for a graph of n edges. We prove a base case, and a convenient base case would be having no edges at all. So the degree is 0, the number of edges is 0. And then we prove that if it's true for n edges, it's true for n plus 1 edges. So it's a pretty straightforward inductive proof. So here's a corollary. An undirected graph has an even number of vertices with odd degree. So here we had exactly 2 vertices with an odd degree. 2 is an even number. We might have 4 vertices with an odd degree, or 6, or 0, but this theorem says we cannot have 5 vertices with an odd degree. It's got to be an even number of vertices with odd degree. Is that believable? So think about modular arithmetic and think modulo 2. So the left side of this equality is 2 times an integer. So this has got to be even, right? 'Cause 2 times anything is even, which means this is congruent to 0, modulo 2. Which means this right side must also be congruent to 0 modulo 2. Well, let's write out what that right side looks like. So degree of vertex 1 plus degree of vertex 2 plus degree of vertex 3. Right, we're going to add up the degrees of all the vertices in this graph. And we want to know what that's congruent to. Modulo 2, well, we know it's got to be congruent to 0, right? Well, if the degree of a vertex is even, it's congruent to 0 mod 2, right? And if the degree of a vertex is odd, it's congruent to 1 mod 2. And so some of these will be 0 and some of these will be 1. But if I had an odd number of vertices with odd degree, I would have an odd number of 1s added to a bunch of 0s. Well, if I add up an odd number of 1s, do I get an even or an odd? You get an odd, right? 7 1s, 5 1s, 3 1s, 101 1s, right? So the only way this sum can come out to be an even number, it can come out to 0 mod 2, is if the number of odd vertices is even. Right, because every time I have a pair of vertices with an odd degree, when I add them together, 1 plus 1 becomes 0 again. And if I have an odd number of vertices with odd degree, I'm going to have a 1 left over. So you can wrap a pretty straightforward proof around that idea and show that the number of vertices with odd degree has to be even. And it's just a corollary of this observation about degrees. All right, so what changes when we have a directed graph? So our edges have a sense of direction. So here's an edge going from U to V. And so I'm writing it as an ordered pair, U comma V. And so here's some of the equivalent things we can say. U is adjacent to V. V is adjacent from U. initial vertex. And V is the terminal vertex. So now we have to modify our definition of degree. So we can do our hunchback D with a little minus sign on top. And this is the in degree of vertex V, which equals the number of edges that terminated V. Or that have V as their terminal vertex. So it's the number of things pointing to V, basically. And delta plus is the out degree. And it's the number of edges with initial vertex V. So things that come out of V. And so here's the corresponding theorem. For directed graphs, so for a directed graph, G equals VE, the sum over all vertices in V of the in degree is the same as the sum of the out degrees is the same as the number of edges.
What was the statement before that?
This?
The outer edges?
So this is the in degree, it's the number of edges going into V, basically. Number of edges pointing at it. And delta plus is the out degree, that's the number of edges leaving a vertex, pointing out. So let's do an example. I come up with such hard examples for myself. I should save them for homeworks.
That's a big example.
That's a big example. Yeah, look at that mess. All right, so let's find the in degrees. So number of things going into A, and looks like that's 0. Everything's going out. So the out degree of A is 1, 2, 3, right? All right, for B, the in degree is what?
3.
3. And the out degree
1.
is 1, good. All right, for C, how many things going in?
1, 2.
Yeah, 1, 2. And number of things going out, also 1, 2. All right, D, how many things in? 1, 2, things going out. All right, how about E? And things going out. I seem to have a pattern in my brain. Okay, F should be different though. How many things going into F? 1, 2. And things going out is 1. So if we add these up, 3, 5, 7, 9, 11, 3, 4, 6, 8, 10, 11. So the sum of the in degrees and the sum of the out degrees match, and the claim is that's also the number of edges. So let's count our edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Did we get them all? Just like Pokemon. All right, we've got 11 edges. Things are good.
Do we have a small example?
Sure. Good with this one for now? Let's do small. Here's a very small example. So number of things going into A is 0. Number of things coming out of A is 1. Number of things going into B is 1. Number of things coming out of B is 0. So the sum of the in degrees is 1. The sum of the out degrees is 1. And the number of edges is also 1. I could add an edge back, and then the in degrees would be total of 2, and the out degrees would be 2, and the number of edges would be 2. Or I can add one more vertex here. Alright, so now in degree of A is 0, out degree of A is 2, in degree of B is 1, out degree is 0, in degree of C is 1, out degree of C is 0. So this adds up to 2, this adds up to 2, and we got 2 edges. And could you prove this theorem as well? How would you prove it? Probably use induction. So if you add one more edge, directed, right, it's going to start at some vertex and it's going to terminate at some other vertex, possibly the same. And when it does that, the out degree of the first vertex will go up by 1, and the in degree of the second vertex will go up by 1, so your sums will still be equal. And your sums will go up by 1, and your number of edges went up by 1, so it's the same induction argument. And so this gets potentially a little stranger when we have loops. Like this. So out degree, or in degree of A is 0. Out degree of A is 1. What do we do about loops here? So in degree of B is going to be 2, because we've got that and that, and the out degree of B is going to be 1. So with an undirected graph, we count loops twice. With a directed graph, we basically count one out degree and one in degree. So the sum is 2 and the number of edges is 2. All right, so standard examples of graphs, because sometimes it's useful to have sample graphs handy. So the first is complete graphs. Of n vertices. And we write this as k sub n, I guess k for complete. So k1 is just a dot. K2 is a pair of vertices connected, so these are undirected. K3 is 3 vertices in a triangle. K4 is 4 vertices, like this. So a complete graph, we have an edge between every pair of vertices, or each pair of vertices. So K5 Alright, so complete graph of n vertices. You have n vertices, and any pair of vertices, there's an edge between them. A cycle C sub n of n vertices is pretty straightforward. It's just something like this. So this is C5, for example. So vertex 1 is connected to vertex 2, an edge from 2 to 3, an edge from 3 to 4, and so on, and an edge from the last vertex back to the first. A wheel, Wn, is just Cn plus one center vertex, and I'm putting center in quotation marks. I'll tell you why in a minute. So if this is C5, W5 would look like this. Right? It's your wheel, your cycle, plus one extra vertex that's connected to everything. So it looks like a wheel if you draw it like that. So one thing I haven't said yet, but I'll say now, when we draw pictures of graphs, our choice of where we put vertices, how we route the edges, are completely irrelevant for the graph. Okay, so from a graph theoretic viewpoint, so here's C4. Right, 4 edges, 4 vertices. But this is also C4. And this is also C4. Okay, you can imagine these edges as being rubber bands, and as long as you don't break the rubber bands, you can move this thing around in any way that you like. So here I've just taken this and sort of stretched it out, and here I've taken this and kind of flipped this over, right? But all of these are exactly the same graph from a graph theoretic point of view. So it's an interesting question, given two of these things drawn on paper, for example, how do you tell if they're exactly the same graph? And for example, the fact that this and this would be the same graph is not immediately obvious, unless you've played with this before, right? So we're going to be interested in knowing how to take all of these different things and store the essence of this graph in a computer so we can manipulate it or analyze it. And so we're going to look at ways to represent this stuff in a computer. And it should be agnostic to how it's drawn on paper, for example. So let me give you a couple of more definitions and then we'll represent these things in computers. So, definition, W comma F is a subgraph of V comma E if W is a subset of V and F is a subset of E. So here's a graph. If I just remove some set of edges and vertices, right, I get a subgraph. And by the way, there's nothing in our graph that says that this is not a valid graph. This is a valid graph. It's not what we call connected. In a connected graph, there's a path from any vertex to any other vertex if we follow edges after edges after edges. And in this case, there's no way we can follow edges to get from here to, say, here. So it's a disconnected graph, but it's still a graph. And this is a perfectly fine graph. It has one vertex and no edges. And in fact, this is also a perfectly fine graph. It's got 5 vertices and no edges. It's not connected, it's not terribly interesting, but it's a graph. So graphs are very general objects. All right, so we have subgraphs. We have a notion of removing an edge. So if we have a graph G and we subtract some edge E, that gives us a new graph with the same set of vertices and just the set of edges. Sorry, these are parentheses. The set of edges with that edge removed. So removing an edge is easy. Right? Here's a graph. If I want to remove this edge, I just remove it. Doesn't change the set of vertices. Right? It just takes one edge out of the set of edges. But sometimes what we want to do is contract an edge. So here we remove an edge. And then basically combine its vertices. So let's see if I can come up with an example. So if I want to remove this edge, I'm going to take that out of the graph, and then I'm going to join B and C together to be the same vertex. So this was 1, 2, 3, 4, 5. If I'm removing edge 5, I'm still going to have edge 1 connecting A and B. But B and C are going to become the same vertex. In other words, I'm taking this edge and I'm shrinking it down to a point where B and C are the same. So now edge 2 connects A to B, and edge 4 connects B to D, and edge 3, which was connecting C to D, is connecting B to D. So there's edge 3. So that's the result of contracting edge 5. And you can kind of see it, right? I mean, we basically took these two things and squished them up together, and that's what we ended up with. All right, and the last operation we can do is removing a vertex. So remove the vertex and any edges incident. So if we want to remove vertex B, we get rid of B, we get rid of all the edges that are incident to it, and so we're just going to be left with the following. And we basically have rid of those three edges. So those are manipulations we can do on graphs. All right, so this takes us up to the question of representing graphs, other than by drawing pictures. So we want to represent these things in a way that doesn't care about how they're physically drawn, for example. So the first approach is an adjacency list. And so this is a table where for each vertex we have a list of adjacent vertices. So let's make one graph to experiment with. So I'm going to have an entry for each vertex, A, B, C, D, E. And for each one, I'm just going to list the vertices that are adjacent. In other words, the vertices that are directly connected by an edge. So which vertices are adjacent to A? B, B. Which vertices are adjacent to B?
C, E, and A.
Yeah, D, C, E, and A. How about C? B and D. D. B and C. And E. And B. Everybody got that? So that captures all the essential information about this graph. And any other way that I draw this graph with any shape, any length of the edges, any position of the vertices, if I make this adjacency list, it's going to come out exactly the same. The order of these things might change, but it's just a set. It's a set of vertices that are adjacent to each vertex, so the order doesn't matter. So that's one way to completely describe a graph. And we haven't talked about linked lists in 224. We'll talk about them in 222. Linked lists are a good way to represent this column. Right? So it's a structure that can grow and shrink, and it's very memory efficient and fairly efficient to work with, storing and retrieving. So that's one way. Another way is an adjacency matrix. So an adjacency matrix, we can use something like a 1 or a 0 or a true or a false to show which vertices are connected to which. So there's no edge connecting A to A. There is an edge connecting A to B. There's no edge connecting A to C or A to D. And there is an edge from A to E. B, there's no edge from B to B. There's one from B to C and B to D and B to E. And so we can just fill in this matrix. So C doesn't connect to itself, connects to D, does not connect to E. D doesn't connect to itself, doesn't connect to E, and E doesn't connect to itself. And I'm missing half the values here, but this matrix is going to be symmetric. Because since A is connected to B, B is necessarily connected to A. So that's going to be a 1. And AC is not connected, CA is not connected, BC is connected, so CB is connected, and so on. So this turns out to be symmetric, right? The matrix is equal to its transpose, means it's symmetric, so you can swap rows and columns. And so I think that's right. And again, this completely captures information about the graph. So one advantage of this, we could use this for a directed graph. And we could say that the entry in BD indicates if there's an edge from B to D. And that would be this cell right here. And this cell over here would be an edge from D to B. So it would be an edge going in the other direction. And then in general, this might not be symmetric about the diagonal. So we could actually store directed information. And that can be useful. The other thing we can do with this is we can store what's called a weighted graph. And a weighted graph is just a plain old graph, but with the added detail that there can be a weight associated with each of these edges. And so if this was a map where the dots, the vertices were cities and the edges were airline routes or interstates or something, right? The weight could be how long it takes to travel along that edge. Right? And you know from traveling that these things don't always make sense. Right? It might take a really long time to go from here to here, and it might take less time to go through this hop over here. Right? Because of some weird reason. So sometimes we have graphs and there's a weight or a number associated with each edge, and we could store that weight inside this adjacency matrix. So instead of simply saying there is an edge from A to B, we could actually store as weight. And weighted graphs get interesting. And they get even more interesting if you allow negative weights. That's where things get really creepy. So network traffic is another good example. Right, so how do you get from your laptop to Google sitting in this room, right? So we hop up to a router and that router goes somewhere else. And that link goes somewhere else and eventually gets out to some big access point. And from there it could go any of a huge number of ways to get to Google itself, right? And it may be that taking some smaller hops gets you to a much faster piece of fiber than if you just take the fewest number of hops possible because you're hopping onto something that's a very slow transmission line, right? So if you're trying to minimize, say, the sum of the weights from one point to another, that's an interesting algorithm. So let me jump off here. So here's your chance at $1 million. Real, not invisible. So traveling salesperson is a famous problem in graph theory, computer science. It's one of several problems that has an outstanding $1 million prize for it. But more importantly, if you solve this, the government will probably pick you up and either hire you or kill you or something. It's a famous problem, and it's really, really simple to state. Okay, so here's the idea. You have a graph that describes a set of cities and the cost of traveling from one city to another. It could be cost in terms of time or distance or tolls or something, but and this can be, fully connected. So you have the cost from every city to every other city. So it's more complex than that, but there's numbers here. Whatever. So here's the problem. You're going to start in some particular city, and your goal is to travel to every other city and then come back to your starting point. And you're told how much time, for example, it takes to get from any city to any other. And your goal is to minimize the total travel time. So in what order should you visit these cities to minimize that sum of these weights? That's the whole problem. And it turns out it's a really simple algorithm to write if you don't worry too much about efficiency. Because from this, so let me label some of these cities: A, B, C, D, E, F, G. So from city A, I have exactly 6 choices. I can go to either B, C, D, E, F, or G. And if I choose to go to B, then I have 6 choices after that. I can go to C, D, E, F, G, or I could go back to A. Right? And if instead I chose to go from A to C, I've got 6 choices there. I can go to D, E, F, G, A, or B. Right? And at each point, I only have a fixed number of choices for which city to go to next. And I can explore all of those options. Right? And as I explore those, I add up how much time it takes. Right? And once I've visited all the cities and I come back to A, I know how long it took with that particular route. And I can find all the possible routes, and then I just pick the smallest total sum, right? The algorithm is really simple. For n cities, it's roughly n nested for loops, right? But the number of ways I can go from here is roughly n, and the number of ways from the second city is roughly n, and it's a total of n times, so this is n to the n possibilities. Okay, so you've got 100 cities, that's 100 to the 100th possible routes you have to explore. Very expensive computationally. Okay, 10 cities, 10 to the 10th. Okay, that's 10 billion. So just 10 cities, it's pretty complex. 20 cities, forget it. You're not going to do it. So the question of the traveling salesperson is, can you find an efficient algorithm for solving this problem? And efficient meaning that instead of being n to the n, it's n to some integer. It might be n to the millionth, but n to some fixed integer in terms of complexity. So bubble sort is like an n squared algorithm. Right? If you double the number of things you're sorting, it takes 2 squared, which is 4 times as long. If you had an n to the 10th algorithm, doubling the amount of data would take 1,000 times as long. But this is still considered efficient relative to that. So the question is, can you find what's called a polynomial time solution? And that's worth $1 million. If you either find one or you prove that there is no such one. And this is a favorite topic of amateur mathematicians, amateur computer scientists, and some not so amateur ones. And there's a really bad movie on Amazon called Traveling Salesman, and it's about solving this problem. And it pops up in science fiction and all kinds of things. And we'll revisit this the last week of this course when we talk about theories of computation. But let me give you the punchline since it's effectively Friday for us. The punchline is there are a set of problems that are extremely difficult to solve efficiently, right? They're just like really, really complex. And there are a set of problems that can be solved efficiently, like bubble sort, right? Or sorting numbers in general, or searching for things, right? And there are some problems that we don't really know. We know how to solve them inefficiently, but we don't know if we can solve them efficiently. And there's a big set of problems that are all roughly the same difficulty as traveling salesperson. In the sense that it's been proven that if you can find an efficient solution to this, you can find an efficient solution to this huge list of other problems. Because you can basically reduce all these other problems to traveling salesperson. And let's see if I have a network connection. I do. Where'd my list go? Oh, this is not a very good. There we go. So all of these things are in some sense equivalent to traveling salesperson. And there's some things in set theory here. There's some things in map coloring. There's some things in graph theory related to finding paths. There's some things we'll do in CSE 222, like the knapsack problem. There's some string processing. There's Battleship. There's Mastermind. There's Minesweeper, Rubik's Cube, Slitherlink, Super Mario Brothers. There's a whole bunch of problems, right? And these are all computationally equivalent to traveling salesperson in terms of complexity. And if you can find a polynomial solution for any of these, you've found a polynomial solution for all of them. And that's one of the millennial prizes. And it's one of those things that kind of changes the world because it's got like crypto implications as well, which leads to bad Amazon movies. Existential theory of the reals. There we go. So it's an interesting problem. And like I say, it's a favorite for non-experts to work on because it's very simple to state, right? Just find an efficient way to traverse through all this stuff. Now, if you have a quantum computer, it's trivial. You can do it in like a single operation. Because a quantum computer can theoretically explore all possible paths simultaneously. And so in the time it takes you to add up one path, you've actually explored all of them, and you just find the one with the smallest sum. So quantum computing changes this, but to do this on a Turing machine or a von Neumann computer, that's the challenge. But it's also one of the reasons that people get excited about quantum is it makes these things tractable. All right, so you got 5 days over break. You can like come up with a solution for TS. I'll give you bonus points if you prove it. How about that?
Okay.
Yeah, right.
Do we have any real homework for me?
Any what?
Do we have any real homework?
No, you don't have any real homework actually, because we're not getting through enough graph theory today. So I'll give you some homework when we come back next week. But yeah, take the time, work on your program, and let's go through a bit more. We got another 5-10 minutes. Let me go through a bit more of this. So an incidence matrix. An incidence matrix is like an adjacency matrix, but we store incidence information instead of adjacency information. So example A B, C, D, E. And here's our edges, 1, 2, 3, 4, 5, 6. So we can store vertices like this. And we'll put edges horizontally. And we basically just list which edges are incident to which vertices. So vertex A is incident to edge 1 and edge 5 and edge 6. And vertex B, edges 1 and 2 are incident. Vertex C looks like 2, 3, and 6. Vertex D looks like 3 and 4, and vertex E looks like 4 and 5. And so you could do 1s and 0s, or trues and falses, or check marks and nothing, or whatever. But it's storing the same information as an adjacency matrix or an adjacency list, right? We can reproduce the graph based on this. And we can do calculations based on these representations. For example, if we want to know the degree of a vertex, what do? We just add up across the row. There's 3 edges incident to this, 1, 2, 3, so the degree of A is 3. The degree of B is 2, the degree of C is 3, 1, 2, 3, and so on. If you want to know the total number of edges, well, total number of edges is just the number of columns in the matrix, number of vertices is the number of rows. And so we can analyze our graph using these different representations. Okay, so let me leave you with a final definition. So 2 simple graphs, G1, which is V1, E1, and G2, V2, E2, are isomorphic. If there exists a bijective map that's a 1-to-1 onto from V1 to V2 such that A and B are adjacent in G1 if and only if f of A, f of B are adjacent in G2. What does that mean? It means you can rename the vertices from one graph and get the other graph.
What's going on? Right there, that says,
Where if there exists a
yeah,
bijection, so a 1-to-1 map from V1 to V2.
what's the word before that?
Bijection?
Bijection.
Yeah. So I claim these two graphs are isomorphic to each other. Isomorphism, same form. Okay, iso, same, morph form. So they're basically the same graph, just twisted around. So our first set of vertices is A, B, C, D. Our second set of vertices is W, X, Y, Z. So to prove that they're isomorphic, we need to form a function that maps from that first set to the second set, and it has to be a bijection, a 1-to-1 onto mapping. And here's what this mapping can look like. F of A goes to W, F of B goes to X, F of C goes to Z, and F of D goes to y. And the claim is these graphs are isomorphic if there's this bijection, okay, 1 to 1, so everything's mapped to exactly once, such that two vertices are adjacent here if f of those vertices is adjacent over there. So A and B are adjacent. That means that W and X must be adjacent. That's true. B and D are adjacent over here, which means X and Y must be adjacent over here. That's true. C and D are adjacent, which means F of C, F of D, Z and Y need to be adjacent. That's true. And AC are adjacent, which means WZ must be adjacent. Right? So anything that's adjacent over here is adjacent over there, and you need to go in the other direction too. And show the only things that are adjacent here are F of A, F of B, where A, B are adjacent here. But really all you're doing is renaming the vertices. Okay, that's what all of that boils down to. F is just our renaming function into saying if we just take A and we call it W and we take B and we call it X and so on, then this turns into that. But that's the formal way of saying it. And isomorphisms are interesting because it is very, very difficult in general, given two graphs, to know whether or not they're isomorphic. Now, sometimes you can prove pretty quickly that they're not isomorphic. For example, if one has 10 vertices and one has 5 vertices, they can't be isomorphic because there's no one-to-one mapping from 10 things to 5 things, right? So if they have different numbers of vertices, they're not isomorphic. If they have different numbers of edges, this condition can't be satisfied. They're not isomorphic. If the sum of the degrees of the edges, or if the set of degrees of each vertex is not the same, they can't be isomorphic, and you can prove that from this definition. So if this has vertices of degree 2, 3, and 5, and this has vertices of degree 2, 4, and 6, they can't be isomorphic. So there's some of these things that we can use to quickly say they're not the same graph, but to prove that two graphs are the same is very complex. Why? Because how many possible mappings are there from vertices here to vertices here? It's a huge number. Basically, this can go to n, this can go to n minus 1, this can go to n minus 2, so it's n factorial possible mappings. And we could take each of those possible mappings and see if any of them satisfy this. And if they do, they're isomorphic. If none of them satisfy it, then they're not. But that's n factorial for n vertices. That's not feasible in general. So we'll look at some ways to show that things are not isomorphic. And we'll talk a little bit more about isomorphism. Okay, so where are we going when we come back? So we'll talk about paths through graphs. So starting at one point, how can you get to another vertex? We'll talk about different kinds of paths, and that will take us into some other interesting areas. And then we'll look at some applications, and then we'll look at some algorithms for not quite traveling salesperson, but for doing some other types of shortest paths. And we'll look at something called Dijkstra's algorithm, which we'll use in 222. So we'll do some of this on Monday next week. I'll give you homework on Monday. And then we're going to go ahead and we're going to switch. We're going to start talking about languages and automata theory and state machines. And that'll probably be our last unit for this course. All right. I will see you next time.